The earlier class on angular momentum, we have obtained the simultaneous eigenfunction of L square operator and LZ operator, and we found that the simultaneous eigenfunction is spherical harmonics with eigenvalue L into L plus 1 H line square y Lm theta pi. This is for L square, and for LZ theta phi. These are the two eigenvalue equation. Note that for a given L, M can have values from minus L to plus L in steps of unity. Let us consider a case that L is equal to 3 angle. In that case, the magnitude of L vector operator is L into L plus 1 H line, and this is root 12 H cross. So this is the magnitude of orbital angular momentum. As for this theory, if we consider this is the z axis, then we draw a semicircle whose it doesn't look like a semicircle. Let me draw. Okay, this is a semicircle of radius root 12 unit. I have omitted the H cross part. So as for this theory, the possible orientations are these: M is equal to 0, then there is this is another projection, M is equal to 1, M is equal to 2, M is equal to 3. These are the possible projections. Similarly, we have this is minus 1, this is minus 2, this is minus 3. So as for this theory, as per the quantum mechanics, the angular momentum operator can have only 2L plus 1, in this case for L is equal to 3, 7 possible directions. It is in contrary to the classical concept. In classical concept, if we consider an angular momentum with a definite magnitude, as for in this case root 12 H cross, then this angular momentum can be oriented in any direction in space, that is any value of theta between 0 to 180 degrees is accessible. But according to the quantum theory, not all values are accessible. Only few values are accessible, and these values are given by this. If we write Lz is equal to L dot k cap is equal to magnitude of L times cos of theta m, because theta m, the angle depends on the value of m, then we get cos of theta m is equal to Lz by the magnitude of L. This is actually becomes the magnitude of Lz operator, and this is L vector operator's magnitude. As per quantum theory, it is mh cross, and the denominator one is L into L plus 1 h cross, so this is m into these are the possible orientations. If we consider L is equal to 1, then we see that ML has 3 values. For M has 3 values, 1, 0, minus 1. Correspondingly, this cos theta value is 1 by root 2, 0, minus 1 by root 2. They corresponds to 45 degree, 90 degree and 135 degree orientations. So for L is equal to 1, the angular momentum can be oriented at 45 degree and at 90 degree and at 135 degree, and there are no other possible directions. This phenomena is known as space quantization, that is, orbital angular momentum has some discrete orientation in space. As I have already pointed out, this is not no such quantization is available in classical mechanics. Also, this theory differs from the prediction of quantum mechanics. Let me write the corresponding prediction of quantum theory that was put forward by Uhlenbeck and Goldsmith. In that case, it is the L operator is not like this. It was the L value. As per quantum theory, the prediction is like this. If we have L is equal to 3 again, it is for L is equal to 3 case, this is also L is equal to 3 case. The projection is this: 0, 1, 2, and this is 3. This is the z-axis. This is z-axis, and similarly and this is 3. So this is -1, -2, -3. This is the prediction. Both are for L is equal to 3. Both are for L is equal to 3. This is the prediction of quantum mechanics. That is, and this is the prediction of quantum theory. That is the theory that was put forward before the advent of quantum mechanics, that is towards the development of quantum mechanics. The difference is that here, in this case, we say that the angular momentum can never be oriented in the direction of z and along the z axis, but here it says that the maximum and minimum projection is along the z axis. This violates quantum mechanics because as we specify the angular magnitude of angular momentum, here the magnitude is the 12 h cross, and here the unit is √3 h cross. So we specify the angular momentum, magnitude of the angular momentum, and as well as we specify that it is along z axis. So we are specifying the angular momentum and its direction, which violates the uncertainty principle. Delta L, delta phi is of the order of h cross. But in this case, this uncertainty principle is obeyed, and if we consider a particular projection, then it is the z axis. If we consider this is a particular theta value, then this L vector precesses over a right circular cone whose semi-vertical axis is given by theta m. So the phi angle, we don't, although we know the value of L, we do not know anything about the phi angle that the orbital angular momentum makes with the z axis. Phi can have any values from 0 to 2 pi. That is, although we know delta L specifically, we do not know anything about delta Z, so their product is a finite quantity. So this obeys the uncertainty principle, this violates the uncertainty principle. And the phenomena is known as this phenomena is known as space quantization, as I have already that is the quantized direction of angular momentum operator in space. Now I come to another part, the angular probability distribution function. We know that the simultaneous eigenfunctions of L and L square and Lz are spherical harmonics. Let me first write few special spherical harmonics we consider as, for example, L is equal to 0 case and L is equal to 1 case, and the other cases are available in literature. It is found that y00, 0, L is equal to 0, so m is 0. This is equal to a constant is equal to 1 upon 4 pi, and there are y10 of theta phi. This is 3 by root pi. This is 3 by 4 pi of cos theta, and y1 plus minus 1 is equal to minus plus 3 by 8 pi sin theta e to the power plus minus 5. We define the angular probability distribution. We write it P of LML of theta is equal to so that P Lm theta d omega gives the probability of finding the particle within the solid angle d omega in a state given by Ylm of theta phi. The reason for writing it for phi only is that Ylm is no, you know that Ylm, the spherical harmonics, is P Lm cos theta times e to the power Im phi. Whenever we take the star of it, it becomes e to the power minus Im phi, and when we multiply these two, the resulting quantity becomes phi independent. So it is cylindrical, has cylindrical symmetry. That is, on the surface, if we make phi is constant in a spherical polar coordinate, this is the position vector r, and phi is this the projection, this angle. If we keep phi fixed, then if we have the quantity independent of phi, then we may consider a cylinder, and on this cylinder nothing changes. So that is the angular probability distribution has cylindrical symmetry. Let me find out the angular probability distribution for P00 of theta. We see that it is 1/4 pi. So apart from cylindrical symmetry, it has spherical symmetry too. So if we like to plot the polar graph of it, this is the z-axis and this is our xy plane, and we see that it is symmetric. For every value of theta, let me denote the value of theta. This is z-axis. If we have a projection along this is the theta. For every theta value, the radius vector is fixed, so it is a semicircle of this form, and whenever you rotate it about the z-axis, a sphere is obtained. That is, we will have a football-like shaft. So this is the spherical symmetric case. Now we consider P10 case. P10 of theta. P10 of theta is 3/4 pi times cos square theta. Now what will be the polar graph of cos square theta as theta changes from 0 to 0 to pi. So this is again z-axis. This is our xy plane. Now on the z-axis, cos theta is 0 and it is a maximum, and then it becomes a 0 at theta is equal to pi, theta is equal to 90 degree, it is a 0, and when theta again increases, it becomes minus maximum at theta is equal to 180 degree. So it is a three-like structure. When it is rotated about z-axis, we get a curve like that. That is when this is considered a sphere, and it is being folded at the middle. That is the solid structure that you will have by rotating 8 about its axis. It is 8, and if you rotate it about this axis, you will have an upper sphere and a lower sphere like behavior. This is the structure, and we will see the books has written the polar graph like this. So this is L is equal to 1, the angular probability distribution for L is equal to 1, M is equal to 0. For P is plus minus 1 of theta, it is 3/8 pi, it is sine square theta. The graph of sine square theta is, this graph will be it is 0 on z-axis. If you draw a polar graph of sine square theta, this is the graph, and when it is being rotated, you will get the other half. So this is the polar graph for this one. Now if we consider the other higher states, it will have the same feature. it is found that for L is equal to 0, now let me conclude, for L is equal to 0, it is spherically symmetric. For L is equal to 0, it is spherically symmetric. For if we consider higher L values too, it is found that for M is equal to 0, the maximum angular probability is obtained on the z-axis. This is because of the fact that for M is equal to 0, the angular momentum is being rotated in xy plane. So the rotating quantity is in xy plane, so its vector direction is perpendicular to the direction of rotation. So it is the maximum probable that it will have a maximum probability on z-axis. This feature is found for all values, that for all L with M is equal to 0, the maximum probability is obtained on z-axis. And as M increases from 0 towards the maximum value, this graph changes continuously to attain the value of this for M is equal to plus minus L. You may consult any book where L is equal to 2 and L is equal to 3 for angular probability distributions are being plotted. And when we will have the map, what is the significance that the curve looks like this when M is maximum? When M is maximum, the rotation takes place along the maximum projection. So it has the particle moves along the z-axis or near the z-axis, and the angular, so the vector direction will be nearly to the xy plane. That is what it explains. These things has been nicely explained in the book of K.S. Crane, Modern Physics. So in this class, what we have covered up is this. One thing is the space quantization, that is angular momentum. In quantum mechanics, angular momentum cannot have any orientation in space. It has only specific orientation, which is not found in classical physics. The space quantization of quantum mechanics is also different from that of quantum theory. In the theory of quantum theory, one assumes that the maximum or minimum projection value is obtained when the orbital angular momentum is oriented either in the direction of z-axis or anti-parallel to the z-axis. But by this we specify both the angle and the angle of rotation and the magnitude of orbital angular momentum quantum number, which is in contrary to the uncertainty principle. So the correct consideration is taken in quantum theory, which says that even for the maximum projection, the angular momentum is not at all oriented along the z-axis, but it presses about a right circular cone with semi-vertical angle theta m, and that is to say that even if we have a specific knowledge about the magnitude of the angular momentum, we do not have any knowledge about the about the phi value. Phi value can have anything between 0 to 2 pi. So the uncertainty principle is obeyed. Secondly, we have considered the angle. Lastly, we have considered the angular probability distribution function is defined like this, and it is found that the angular probability distribution has cylindrical symmetry. In general, have cylindrical symmetry. For L is equal to 0 case, it has spherical symmetry also, because the angular probability distribution doesn't have any theta phi dependence, no theta phi dependence. For L is equal to 1 and M is equal to 0, this is the probability distribution, so it looks like this. And for 1 1 it is like this. The physical meaning has been explained. In this case the particle have zero projection, so it is rotating in xy plane, so its vector is directed along this. And in this case the maximum projection is along z axis, so the vector notation is perpendicular to z axis, not exactly perpendicular, nearly perpendicular. And as we move from m is equal to 0 to m max, this progressively changes and comes to this. As for example, for L is equal to 2 and M is equal to 1, the curve looks like this, which is intermediate between this and this. And for L, this is for L is equal to 2, M is equal to 1. That's all for the angular momentum theory using Schrödinger picture and its interpretation. In the next class we shall consider the Heisenberg treatment of angular momentum, which will enable us to include spin as well in the quantum theory.